Okay, so we agree that isothermal processes are a good idea because we get the best return on our investment. But they can't all be isothermal processes because then we get no return. So what should the other processes be? The Otto cycle uses two isovolumetric processes. The diesel cycle uses, I think, one isovolumetric and one isobaric process. How much better is the diesel cycle than the Otto cycle? And in order to answer that question, we need to define what we mean by better. What is efficiency? And we've hinted at this already, that we are interested in the work, the useful work done by the engine as a fraction of the investment of energy that we made, QH. Find the ratio, and that's the efficiency written as a decimal. If you want percent, you can multiply by 100. The work done is whatever the difference is between the heat that's transferred in and then the heat that's transferred out as exhaust. So W is the difference between the heat transferred in and the heat transferred out. It's whatever other energy there is. It has to be sent out of the system as work on the environment because it's a cycle. We have to get back to the same temperature. Delta U overall for one cycle has to be 0. So the Q needs to be equal overall to the W. If we're Qing in and then Qing a little bit out, the net Q is equal to the net W. And that's what that numerator there is about. We can simplify that 1 minus the ratio of heat. If we are transferring QL out of the engine as exhaust and transferring QH in, likely by combusting some sort of fuel, releasing some heat from that reaction, the ratio of those 1 minus that gets us the efficiency. What's the best we can do? What's the right choice? You know, we have those 4 types of thermal process. We can choose what to do, when, and which process, and what's the best way to do this? How do we maximize the efficiency? To answer that, we turn to the work of a French engineer, Sadi Carnot. And Carnot realized something fundamental about the different kinds of thermal process. They're all categorizable into one of 2 categories. That's it. Let's look at an example. Suppose we have a metal container that contains ice. The ice is at 0 degrees. The metal container is at 70 degrees Celsius, let's say. The ice and the metal box will reach thermal equilibrium because they are in contact, or because the metal radiates thermal energy to the ice, or something like that. Suppose they reach thermal equilibrium at 40 degrees. This never happens backwards. There's no way that we put a room temperature object, 40 degrees Celsius, we set a cup and a metal box and water at 40 degrees, all of it. We set it on the table. It never happens that the heat flows the other way, that on its own, the ice, the liquid water cools down and refreezes, and the metal box heats up. That never, ever, ever happens. We can't turn that around. The only way to cool the water back down is to cool down the metal box. But if we're cooling down the metal box, it doesn't end up at 70 degrees. There's no way to unpack the thermal equilibrium that we ended up with. It is irreversible. Contrast that with a situation like this. Suppose we have ice and a metal box at 0 degrees. Here, we can just sort of nudge the system one way or the other. We can drop in a little bit of heat and melt the ice. And we can cool the system just a little bit, expose it to just a little bit of something colder, and coax the liquid water to refreeze. And we can do that back and forth and back and forth. And there's nothing that prevents us from doing that. We heat it a little bit, we cool it a little bit by just ever so slightly changing the temperature of the metal box. I mean, it's still basically zero. It's just like 0 plus or 0 minus. We're just nudging the system one way or the other of its equilibrium. There's no way to do that here. We're stuck. We've got 40 degrees. We can't cool down the metal box just a little bit and have anything happen. I mean, it'll eventually they'll reach a thermal equilibrium, but it won't refreeze. There's nothing we can do. Some small amount, we can't, there's nothing we can do. This we can reverse. This is it's an example of a reversible process. Carnot realized that processes that are reversible are very efficient because we can get back everything we put in. We can turn it around. It's fine. We can do that. Irreversible processes are inefficient. Whatever our initial investment was, heating up the metal box to 70 degrees, that energy is gone. It's not gone. It transferred into the water, melted it, and increased its temperature. It's still there, conservation of energy. It didn't disappear, but we can't get at it anymore. We can't pull it back out of the water and heat the metal back up. That's not how this system works. This is inefficient. So Carnot's decision was to build a theoretical engine on paper using only reversible processes, only very, very slow sort of equilibrium processes, very, very, very small changes in temperature, very, very, very small, infinitesimal, right? Infinitesimally raising or lowering the temperature. If we use processes like that, then we should be getting out. We should be able to recoup almost everything we put in. Isothermal expansion. Change the temperature very, very little. Isothermal is good because we get all of the work out that we put Q in. Isothermal is good. Adiabatic, because once we make our investment of QH, I don't want to have to add any more heat. Adiabatic, no heat is transferred. And we let this all happen very, very slowly so that there's no turbulence. Everything's very, very gentle. Everything is reversible, at least in theory. Then isothermal, and then adiabatic again. So isothermal to do some work, adiabatic to move things around without adding any more investment, without transferring any more heat than we had to. Here's a diagram of the Carnot cycle. And using a handful of calculus and differential equations, we can show, well, Carnot was able to show that this is the best we can do. That this is theoretically the largest possible area of net work using an ideal gas between state A and state C. This is the best we can do. And it's the best we can do because these processes are all reversible. We could turn this around and it would work just fine the other way. I don't know why we would do that. What we wanted was a heat engine, but the theory is that all of these processes are reversible. If we use such a process, we can also show that the efficiency is expressible this way. Instead of 1 minus QL, where'd that slide go? Instead of QL and QH, Carnot is able to show that the efficiency only depends on the temperatures of that high temperature and low temperature reservoir. The temperature that the highest temperature that the working substance, after we burn the gas in the engine, the hot temperature that's created, and then the temperature at the end where that we expel our thermal energy into. We could get to a 100% efficiency if the term there, TL over TH, were 0. The only way to do that, well, okay, so there's 2 ways, well, there's 1.5 ways to do it, and I'll start with the half. What if we make T sub H stupid hot, like tens of thousands or hundreds of thousands of Kelvin? Whatever the low temperature is, even if it's 300 Kelvin, 300 over 300,000 Kelvin, that term is so small. 1 minus that is basically just 1 again. 1 minus really, really, really small is still, what, it's 0.999999, whatever. That's basically 100%. The trouble with that is that we're limited by the materials that we have. The engines that we're using can only be so hot. If your engine in your car melted when you tried to use it because the internal temperature was trying to go so high, that wouldn't be very useful at all. It'd be super, super dangerous. The other problem is that the hotter we get that working substance, the ideal gas, the greater the pressure it exerts on its container. And then the whole thing could explode too, just tear itself apart. Again, not ideal. The only way, really, to get this equal to 1, to get an efficiency of 100%, is for TL to be 0. 0 Kelvin. Only if the cold reservoir is at absolute zero, which is impossible. That this the slide just says that. Is it impossible? Why would it be impossible? Imagine that you are trying to cool down a glass of water. If I want to cool down this seltzer water, I can add ice. I can go find a thing that is colder, introduce it to the system, and the colder thing and my system will reach a thermal equilibrium at a temperature lower than my system originally started. Then I need to go find, more ice or something else colder. I got to go find some liquid nitrogen or some, I don't know, liquid helium or something very, very cold, and expose my system to that to try to lower its temperature. Now, the lower we get, suppose we do have liquid helium, 4 Kelvin. 4 Kelvin. Now, how do we cool that down? We got to go find a thing that is colder. How hard is that going to be? We got to spend all this time engineering a thing that is 3 Kelvin, only to expose it to the liquid helium and have them reach an equilibrium at 3.5. All right, now we're at 3.5. We got to find something even colder to lower the temperature even further. How are we going to get to zero that way? Even if we had a whole pile of stuff over there that had a temperature of absolute zero, we take it spoonful by spoonful and put it in the seltzer water. As the seltzer water freezes, fine. Now its temperature is, I don't know, 10 Kelvin, and we keep adding absolute zero. We add a spoonful, now the temperature is 9. And then we add another spoonful. Well, suppose we're adding equal masses, right? Suppose we start at 10, we add some stuff, then they reach an equilibrium between 10 and 0 at 5. Then we add some more and it 2.5. Then we add some more and it's 1.25. Then we add some more and it's whatever half of 1.25 is. And then we add some more. And you can see where I'm going with this. Every time we add more and more and more and more stuff at absolute zero, we're only decreasing the temperature by fractions of a degree. First we have a quarter, then we've got an eighth, and then we've got a 16th, and then we've got a 32nd, and we're never going to get to zero by dividing by 2. It's never going to happen. How are we supposed to achieve absolute zero? If you had a thing at absolute zero, how would you know? You'd take your thermometer and you stick it into that environment, and your thermometer, which you just had in the room with you at normal temperature, is going to bring a whole bunch of thermal energy into that absolute zero environment, and now it won't be at absolute zero anymore. How would you even know that its temperature was absolute zero? And how would you keep it there? How could you perfectly insulate it from everything? That no contact, no radiation could get to it. If you put it in a box, in a box, in a box, in a box, it would have to be infinitely insulated so that no thermal energy could be transferred to it. What? Infinite insulation? That's not gonna. Depending the resource you use, the third law of thermodynamics is that no system can reach absolute zero in a finite number of thermal processes. No matter what we do, if we transfer 0 Kelvin, even 0 Kelvin stuff into this, there's no, we keep dividing a positive temperature by numbers, it'll never be zero. That's the problem. The only way we can make it be zero is in the limit as we did infinite amounts of cooling. Eventually, it's 0.00001, which is basically, I mean, at a certain point, it's zero enough. But that takes an infinite number of cooling steps. If no system can reach absolute zero, and certainly not in any kind of usable way, then the low temperature, the temperature of that cold reservoir, the environment into which we are throwing our leftover heat investment to get back to square one to start the cycle again, has to be greater than zero, which means the efficiency cannot be one, ever. The third law of thermodynamics, that no system can reach absolute zero in a finite number of processes, is, depending whom you ask, it's actually the same as the second law of thermodynamics. And the second law of thermodynamics is basically just this conclusion we've reached: 100% efficiency is not possible. It is not possible for an engine to entirely convert thermal energy into work and nothing else. There will always be some byproduct. There will always be some QL that needs to be exhausted, because that's where we ended up. We cannot make the efficiency one. It's not going to happen. The efficiency will never be one. Perfect conversion from our heat investment to work done isn't possible. That's the second law of thermodynamics. There are a bunch of ways to say it. Heat flows on its own from a hot object to a cold object. It will never do the same on its own. And this is another way to say what we've already said about a process like this. The thermal energy flows from the metal box to the ice, not the other way around. The ice in that metal box will never spontaneously cool down in order to further heat up the metal box. And that's the problem we have here. This liquid water at 40 degrees will never on its own cool down, releasing thermal energy into the metal box to warm it up. It'll never happen that way. That's another way to say heat will flow spontaneously from hot to cold, not the other way around, which is another way to say that no engine can be 100% efficient, which is another way to say that no system can reach absolute zero. Let me go back again to the slide about the two metal boxes. The thermal energy, the heat flows from the metal box into the ice. That's energy, and it lives in the system. It didn't go anywhere. It didn't vanish. It didn't get destroyed. It's still there. Energy conservation is totally still satisfied. But that thermal energy is no longer useful to us. It's like when you rub your hands together when they're chilly to get friction to create heat to warm your hands up. You spend some energy to do some work to move your hands, and that friction releases thermal energy. That thermal energy, it still exists. It's just you can't get at it anymore. You rub your hands together and then you hold them in the air, and that thermal energy you created dissipates into the air. And you could scrape all the air back together, and but you can't unrub your hands. You can't take the energy back out of the liquid water and give it back to the metal box. It doesn't work that way. It's like there's only one way. Well, yeah, I mean, an irreversible process only goes in one direction, right? It goes this way. You cannot turn it around. You can't reverse it. It only goes in one direction. A broken coffee mug lifts off the floor, reassembles, and lands on the table intact. Right? I mean, if I film a mug falling and breaking, and then reverse the footage and show it to you, you know that it is reversed. You can say, you see it and you go, oh, well, that's clearly video that's been reversed. We can we can reverse the video, but we can't reverse that process. Things that fall and break, you could stand there and watch it forever. It'll never hop up off the ground in all its pieces and reassemble as a whole object again. It'll never happen. We understand that this is a process that happens in one direction. Something about this breaking coffee mug is getting at the same idea as irreversible thermal processes. It only goes in one direction. A long time ago, at the beginning of the semester, very early on, I promised that I would share with you my dad's favorite joke. You may have wondered why in these videos there is a banana on my whiteboard here. And the answer is that I need it. It's a prop for the joke. And the joke goes like this: time flies like an arrow. Fruit flies like a banana. I don't know if the joke was worth waiting for, but my dad loves that joke, and I got it from him, and I love that joke. And it's raining really hard. Excuse me one second. And I close that window. Goodness. The reason I wait until now to tell that joke is not because of the banana part, which is funny, but because, or arguably funny, but because of the first part. Time flies like an arrow. When we hear the joke, we have absolutely no problem with that. We say, yeah, time flies like an arrow, and we sort of because I introduced it as a joke, we sort of instinctively wait. It was okay. That was the setup. Where's the punchline? We take for granted that time does fly like an arrow, and these pictures are part of the reason why. Objects do not spontaneously reform when broken. It's not a thing that happens. We understand that whole mug falls and breaks. That is the direction that time goes. I never see it happen the other way around. Change occurs towards the breaking, never the other way around on its own. If we want to sit down and like glue the pieces together, that's fine. But if you just leave the pieces on the table, they never spontaneously reform. The change that we see doesn't go that way. It goes towards the breaking. I'd like to play you a song. You might know the band Muse, and if you don't, just take my word for it that this is an actual band. It's not like it's some joke physics band that I started with another professor in my garage. It's it's an actual band. Like they release albums and go on tour and provide tracks for movie scores and things like this. It's a real group. You can Google it. And the reason I provide all of that setup is that they have an album called The Second Law. And it's called The Second Law because of the second law of thermodynamics. It's an entire album about thermodynamics. I am electing not to share my screen because it has the music video that goes with it has politically charged imagery. So I won't present it here, but it's the song. The band is called Muse, and after a bit, I'll tell you the name of the song. So if you want to view it, you can. The important part and the reason why I'm playing it for you is coming up here in a second.
All natural and technological processes proceed in such a way the availability of the remaining energy decreases.
All natural and technological processes proceed in such a way the availability of the remaining energy decreases, which is exactly what we said about that irreversible ice melting. The energy exists, it's no longer available to us. We no matter what we do, we can't pull it back out of the water, refreeze it, make it ice, and give that energy back to the metal box. It's never going to happen that way. Certainly not on its own. All natural processes proceed in such a way the availability of the remaining energy decreases.
In all energy exchanges, if no energy enters or leaves an isolated system, the entropy of that system increases.
In all energy exchanges, if no energy enters or leaves an isolated system, the entropy of that system increases. Entropy is a new word, and we're going to have to define that in a second. But let's see what else is here in the this introduction to this song here.
Energy continuously flows from being concentrated to becoming dispersed and spread out, wasted and useless.
Energy continually flows from being concentrated to being dispersed or spread out, useless. That it's there, but we can't get at it. We have spread the thermal energy of the metal box throughout the melted ice, and it's useless. It's all spread out. We can't sort of, if we can put a bunch of energy together in a space, then we can use it to do a thing. But if it's all sort of spread out everywhere, we there's not enough in any one spot to do any one thing. It's not of use to anyone.
Grade energy is being destroyed. An economy based on endless growth.
If new energy can't be created, and high grade, the concentrated, useful energy is being destroyed. And I don't like the word destroyed here. The energy isn't being destroyed, it's being degraded. The high grade, concentrated, useful energy is being degraded so that it is dispersed, low grade, non-useful energy.
Right, is unsustainable.
That's enough. Unsustainable is the name of the song, in case you're curious. And yes, the entire album is in fact about the second law of thermodynamics, which I think is just amazing. Really, really cool. Okay, so what is entropy? And the deal is that entropy is a measure of disorder. How disordered is a system? Think about the ice in the metal box. As a solid, ice is a crystal structure. The hydrogen and the oxygen molecules are very well ordered in a very particular way. It's highly ordered. If we melt the ice, then those liquid water molecules are all over the place. They can flow and they have some innate motion according to their temperature, and they're moving all over the place. Much, much less ordered. If you are at a particular location in the water, the chances that you find a molecule right there where you are when you go to look for it are not as good as they are for the ice. If you're standing in the ice crystal structure, you look down, there's a molecule there because, well, it's not going anywhere. I mean, if it's there now, it'll be there later. Yeah, maybe it'll jiggle a little bit, but it's not really going to go anywhere. It can't. It's in a rigid, solid lattice. But in a liquid, they can move, and it's much, much less ordered, which, according to this definition, means that the liquid has greater entropy. And it's entropy and its increase that tells us the direction of natural events. Events occur towards the breaking, towards the mug falling and breaking, never the other way around. We take an ordered whole mug, drop it, it breaks into several pieces, less ordered, like literally messy. That's entropy. Okay, let's make a mathematical definition. Let me go back to the slides here for a second. This one. Okay. Let's define the change in entropy S, like for second law. If a thermal process occurs when Q is transferred, some amount of heat is transferred at some constant temperature T, the temperature at which that process occurs, then the change in entropy, delta S, is the ratio Q over T. All right, so let's think about an adiabatic process which transfers no heat. Delta S is 0. Let's think also about an isothermal process that transfers some amount of heat and does some amount of work. The heat transferred divided by the temperature of the system, isothermal, remember, same temperature, that delta S is positive. And we have, with this equipment, another way to restate the second law. An isolated system has entropy that never decreases. And that's another way to say that there was that voiceover in the song that if no energy enters or leaves an isolated system, the entropy increases. It's possible that we can use only reversible processes like adiabatic processes where the Q is 0, so the entropy change is 0. If we use only reversible processes, it's possible that the total delta S could be 0. And in fact, we can show that that's true for the Carnot engine. The entropy change associated with the isothermal expansion is exactly equal to the entropy change associated with the isothermal compression, and the adiabatic processes don't add any entropy, so the net change in entropy for the Carnot engine is 0. So I guess technically it doesn't have to increase like the line in the song, but it is true that it cannot decrease. The only way to decrease the entropy of a thing is to do work on it from outside. If your room is messy, if there's stuff everywhere like there is in this office, that's why I'm not showing you. Then the only way to increase its order is to enter the system and do work, like literally do work to clean it. To reorder it, to move things around. If the system stays isolated, if there's no way to do work on it, then the entropy will never decrease. Natural processes move toward a state of greater disorder. And that's why time for us, because this is how, like, physiologically we are wired. Neurologically, physiologically, we are constructed in such a way to perceive the direction of change in this direction, towards the direction of greater disorder. Entropy is why time flies like an arrow. We can see, we can see things happening that look like they don't obey this law, and that's because that they aren't isolated. They live in the rest of the environment, the evolution of a species, the growth of an individual. Sure, that's increasing order, but it's as a part of a larger system, and as part of a larger system, the entropy will never decrease. Processes will occur that are not reversible, and movies that run backward look silly. Some energy becomes unavailable to do work. Just really quickly finishing up chapter 15. The pressure, volume, and temperature of a gas or a system are manifestations of the molecular properties of that gas. They have to do with the average molecular kinetic energy, state variables, right? The entropy changes depend on the temperature. So we could say that entropy is also a state variable in a certain sense, which makes me wonder how it is an expression of the molecular properties of that gas. How does the individual motion change the entropy S? And we've already said a little bit about this when we talked about the ice and the water. The ice is in a rigid crystal structure, and the water is not. But maybe we can be a little more precise about that. Let's talk about ways to do a thing. If we toss 4 coins, if we flip 4 coins, there are only 5 possible outcomes. If we get 4 heads, we get 3 heads and 1 tail. We get 2 heads and 2 tails, 1 and 3, or 4 tails. Those are the only possible ways that we can flip 4 coins. There are only 5 things that can happen. But there are 6 ways for one of those outcomes to occur. If we are in the state of 2 heads and 2 tails, how do we know what is the actual sort of individual state of the 4 coins? We've got a 16% chance of picking the actual sequence of coins that are, got us into this state of 2 and 2. If we are living in this state that is 4 heads, there's only one way to do that. That's very, very ordered. If we are in this state, we know what the coins are. We know it. Very ordered. If we are in state 2 heads, 2 tails, that's the least knowable of the 5 states we can be in. There is a 1 in 6 chance that it is whatever we think it is at any given time. Suppose we flip 100 coins. No, because we're headed towards like, okay, what if there's a mole of molecules, and we're asking about flipping a mole's worth of coins to figure out which molecules are where at any given time. By far, the most likely macro state is 50 and 50. 50 heads, 50 tails. The probability is relatively low because there are still a whole bunch of things that could happen, but it is the greatest probability, almost by a factor of 2, from the next most likely in the list, 55 heads and 45 tails. Change by 5 heads near the middle, and again, there are so many ways to achieve 55 heads and 45 tails. Imagine all the different ways to write it. Turns out there are 6.1 times 10 to the 28 different ways to do that. So actually, on second thought, don't try writing them out. Some macro states have very low probabilities. And those are the ones that have the least number of ways to achieve them, the lowest entropy. It's not that the it's not that the thermal process there where the mug jumps off the floor in pieces and reforms on the desk. It's not that it's impossible. It just has a really, really, really low probability. So low. I mean, this is for 100 coins. Imagine how low the probability gets if we want to talk about an entire coffee mug's worth of molecules. Some processes have an extremely low probability, which is like they're never going to happen. And that's another way of talking about the second law of thermodynamics, the process that has the most ways for it to manifest. That's the way things are going to go. And think about the different ways that a mug could break. There's only one way for it to reform, which is a huge reduction in entropy. There's only one way for it to be an entire mug, but there's an almost infinite number of ways that it could break. That's the way it's going to go because there are so many ways to achieve breaking. That's the direction of entropy. It's less ordered now than it was before. The second law of thermodynamics fascinates me because it is a law completely unlike the other laws we've seen. Every other law, it seems like, has been a law about the conservation of energy or of momentum or angular momentum or conservation of mass in like the fluid flow in a pipe. The mass flow rate needed to be the same. All of our rules so far have been about what needs to be the same, what is true, what is possible, what is knowable, and the what is equal. The second law of thermodynamics is explicitly about what must be unequal, what must be impossible, or really, really, really improbable. The fact that the entropy is explicitly not conserved, it must increase, or at the very least, we can construct a corner case where it doesn't increase, but it cannot decrease. That it's a statement about what isn't possible. The fact that we will not get equal work for an investment of heat in an engine. It's not going to happen. And it just feels so strange to bump into the second law of thermodynamics after 14 other chapters of laws about what is equal. This is a law about what is explicitly unequal. Small wonder then that this is the law that tells us how to perceive change. Change, being the idea that a thing is other than it was. That's that's entropy, right? Because that's the direction it always goes. It always goes in the direction of increasing disorder. To be other than it was is to be less ordered. That's entropy, and of course that's how we perceive change, because that's the thing that changes. Everything else is constant. Energy and momentum and all this stuff, it's all conserved. But this is different. that's all I have. Thanks, everyone. Appreciate your sticking with us this semester. I know it has not been easy. Um, I really, really appreciate it. Um, Appreciate also your putting up with the joke about the banana. Um, that's all for now. I'll post these segments and the slides that I used and the worksheet, and that'll be the story. All right, thanks.